And so our next talk will be given by a local, Virgil Marionneau from ENS Rennes, about probabilistic programs.
I have a problem. I've just implemented skip lists as part of some big project I'm working on, but I'm not too confident that I did it just right. So I want some way to be sure. Thus, I go to my good friend Félix, and I ask him if he has some way to verify that my program does what it is supposed to do. He tells me then that I should probably look into the iris separation logic, because it's nice, it's high order, it's highly modular, and I should be able to tailor it exactly to my needs. But I chose to go the random way with my implementation, as it's quicker to write. And I have no idea how to make iris comply with randomness. But he does. He tells me I should look into error credits and the logic that implements them. So let's take a step back and generalize the problem. A lot of algorithms make use of randomness as a way to gain speed at the cost of having correct result up to some probability. And to reason about those algorithms, you need to have specialized logics, such as errors. But such logics only provide one primitive kind of distribution, usually. And different algorithms can sample from different distributions, sometimes multiple at the same time. And thus, you have to implement them before being able to reason about them. And this is a problem because you still want to be able to use them as modularly as the primitive your logic provides can be used. So let's start. Our choice will be errors. So let's start with a primer with what errors is. It is a higher order separation logic that allows you to prove properties about sequential probabilistic programs. The way errors achieve this is by introducing a new resource called error credits, where it will be written using this little lightning bolt, and where owning epsilon error credits is akin to having an allowance to fail to prove the specification under scrutiny with probability epsilon. Errors also comes with two kinds of Hoare triples, total and partial ones, depending on whether you consider a diverging program to satisfy no specifications at all or to satisfy all of them. And the key thing that makes error tick is the fact that whenever your program is sampling from a random distribution, you can choose how you distribute credits depending on the outcome, and you can scale them up or down under some conditions. Let's have a deeper look at how this works. Here are some rules of errors. The first one simply states that you can combine and split credits however you see fit. The second is the one that allows you to make real use of credits. That is, if you have one full credit, then you have the authorization to fail to prove your spec with probability 1. So you can prove bottom and you can stop reasoning at this point. And the last rule is the one that lets you distribute credits. This states that if you start with some amount epsilon of credits and you're sampling from the uniform distribution on the integers from 0 to big N, then you can choose how many credits you want in the end, as long as the expected value of the credits after sampling is at most what you already had. Intuitively, this boils down to saying that if you know that you will fail to prove your spec with probability epsilon, then you can explain why and where this failure can come from. Errors also has two nice adequacy theorems that ensure that what you prove with it has some meaning. The first is for partial triples, stating that if you start with some credits, some epsilon error credits, and prove that your program should terminate to a value v respecting some spec phi, then the probability of the program terminating to a value that does not respect phi is at most epsilon. And for total triples, in the same situation, then the probability of the program terminating to a value that does satisfy the spec is at least 1 minus epsilon. Let's look at a small example to be more familiar with how this works. Here I have a simple program that samples 2 random bits and then checks whether the sum is 2, that is, that both are 1. And if you look at it hard enough, you can convince yourself that with probability 1/4, it should return true. In errors, then you could state the following spec. That is, if I allow myself to fail to show my spec with probability 3/4, I can then guarantee that the program will return true. We can prove it in the following way. We start with 3/4 credits. Then we sample a random value into x. So 2 possible cases. X is 0 or x is 1. In the first case, I will choose to now have 1 full credit and stop reasoning on this branch. In the case x is equal to 1, I will have 1/2 credit remaining. And if you look at the expected value of the credits after sampling, it's indeed 3/4 the amount we had before. On the second branch, we haven't finished reasoning. So we need to sample the second bit into y. Once again, if y is 0, I want 1 full credit and to fail to prove my spec. And if y is 1, I have no credit remaining, but that's not a problem because indeed, in this case, x plus y will be 2, and I will return true, allowing me to prove the spec at the bottom. But now, if you were to take this example and sample from another distribution, first you would have to implement it, and you wouldn't have such nice rule to reason about it. And this is exactly what we set out to do. We set out to define exactly the kind of rules we want for a sampler to be able to use it in exactly the same way and for them to be as nice. And after defining an interface, we have also implemented it using the same methodology over and over again for a variety of distributions and proved some nice abstract results that allow you to get stronger reasoning principles on samplers that implement this interface. So let's get back to what I was saying. I want to replace my sampling by another distribution. Let's say a Bernoulli distribution. So I have to implement it. This would implement the Bernoulli distribution with parameter p over q plus 1. To implement it, what you do is you sample a value from the interval from 0 to q, and you look whether or not you landed before p or after p. And then you return 1 or 0, depending on this. And now that I have this implementation, I can plug it in. And I would be able to prove, probably able to prove with some probability that this returned true. But first, I want some rules to reason about my implementation. Can we maybe find a rule similar to the one we had before? The answer is yes. We can prove this rule for credit distribution, which in a sense is the same thing. We're stating that we start with some amount epsilon of credits, we sample, and then there are only two possible outcomes. Either it is 0 and then I have some amount epsilon 1 of my choice of credit, or it is 1 and I have some other amount epsilon 2. And they are constrained by the fact that the expected value of those is epsilon, according to the expected value for a Bernoulli distribution of parameter p over q plus 1. And this is nice. Then probably this rule can be proven in most of the cases and you want it. But do we really want it, and is it enough? The answer to this is yes. There is this nice theorem we managed to prove called distribution adequacy that states that whenever you have some expression E and some distribution mu, and that you can prove a rule of the shape we've seen before, that is, starting with some credits epsilon and reducing E, we land on a value V and some new amount of credits, such that the expected value of the new amount under mu is exactly what we had before, then the expression has probability mu of V to reduce to every specific value V. So this, in a way, this rule perfectly internalizes the output distribution of an expression. And so we want it in our interface. So we can start building it. We will want some sampler, we will call it sample, and we want it to follow this exact rule. But now that we have managed to generalize one of the reasoning principles Aarhus gives us, we might want to look at the others that I have skipped for now that allow for even nicer proofs. We will be looking at pre-sampling tapes. These are a device that allow you to completely decouple reasoning about credits and sampling from the actual flow of the program. The way you achieve this is by extending your operational semantics with a new kind of state we call a tape. A tape will have a label, which is a kind of abstract location, and it will represent some source of randomness for which we have already received some values. So if I have some tape at a location iota, but it is empty, and I am sampling from that exact tape, then as I have no bits already sampled, I will simply reduce, as before, randomly. But if in my state I already have some values on iota, then I will reduce deterministically with regards to the value on the tape. And I will remove this value b from it, as we want to note the next samples to be sampled if we call again. The reason this doesn't affect the adequacy theorems for Aarhus is that there is no way for the language or the program to add stuff onto the tape. We can only do it at the logical level. And so, if I have, in my logical context, the fact that some tape at the location iota has values on it, I can go from this to having two new possibilities for the uniform distribution on 0, 1, whether I have the same tape with the value 0 appended at the end or the value 1. And I can resume reasoning from there. Let's go through another example to understand how this can be useful. Let's see the rules first, sorry. So you have the first rule that simply states that you have a language construct that lets you, at the logical level, allocate an empty tape. Here the hooked arrow is basically a points to predicate, but for tapes. The second rule states that, as we've seen before, if the tape has already some information on it and we are sampling, we have to return the value that the tape holds and remove it afterwards. And finally, the last rule states that we can do reasoning with credits whenever we presample values onto the tape, as we've done before when sampling from the program, but now purely logically. Now let's get to an example. I've taken here the example from before, but I've made the bit sampled into X lazy. It will only be sampled when we really need it. And so at this point, I can't really do the same reasoning I've done before, because when I reach X, I have no way to split credits by sampling, because the program is not actually sampling. But luckily, I've labeled the sampling operation with a tape that I allocated before, and I can still prove the same spec as before for my example. The way this would be done, again, is you start with 3/4 credits. Then you go through the tape allocation and you get an empty tape at some location iota. Then you make the conscious choice of sampling onto the tape, whether you append 0 or you append 1. And you can do exactly the same reasoning for credits as we've done before in this situation. So the leftmost branch can be eliminated right away. But on the rightmost branch, we still have to work again. So we can go through the regular sampling and scale credits as before, eliminate the new leftmost branch, and now remains the branch where X and Y, where Y is 1. But now we have some value on the tape. So when I will reduce X, the tape makes it so that it reduces it to 1 necessarily, and I can still conclude. And I can keep the nice flow of credit reasoning I had in my previous proof. So can we maybe generalize this idea to the Bernoulli example we had before? So the first thing we want is some way to label tapes for this example. So we will modify the implementation slightly to take a tape location as input and label the sampling operation with it. Then allocating a tape for this sampler will boil down to allocating a tape for the innermost sampling operation for the uniform distribution. So the implementation is simple and as follows. The interesting part is defining what it means to own a tape for the Bernoulli sampler. It will be done as follows. Owning a tape for my sampler at location iota with the bits from B onto it will amount to owning a tape for the uniform operation I'm doing inside of it, such that when I translate what it means to run the sampler with those values from the innermost tape, I get the values I want to hold outside of this existential. And if you work through those rules a bit, you will be able to prove reasoning principles similar to the ones from before. I will not show them for this example, and instead show directly what they are in the general case. And here is an example of a tape and what it translates to. So in our interface, what we want now is some way to allocate a tape. We want some notion of owning such a tape at the logical level. We want indeed that when we run through the allocation, we do get an empty tape at some location. And we want that if we are sampling from some location and at this location a tape holds some value, we reduce according to it. And finally, we want to be able to pre-sample onto the tape. As before, again, we want to be able to start with some credits and go to a situation where we have one more value onto the tape and credits according to what this value is, as long as its expected value is the one of the credits we had before. But now that we have this nice little interface, we might want to put it to the test. So let's go through a case study of the geometric distribution. It's interesting because for now the example I've used had a finite support and was always terminating. But here, the geometric distribution has infinite support. And as you can see from this implementation, it can have arbitrarily long runs. So it's not terminating anymore, but only almost surely terminating. But Aris has some tooling that lets us still prove some things about this kind of implementation. The main technique we will be using is called error induction. As it is a bit complicated, let's take a small aside to understand it better. The rule for error induction on error amplification or error induction is as follows. It's not the most understandable, but let's try to understand it intuitively for maybe the example of recursive function. This here states that if you want to prove something about a recursive function, and before reaching any of the recursive call, you can strictly increase your credit by a constant amount, greater than 1, then two things can happen. Either you do finitely many recursive calls, and so you terminate and you just have to prove the spec. Or you do infinitely many. But as you keep increasing the amount of credits, you have to reach 1. And when you reach 1, the proof can still terminate, and you can again prove your spec. And once we know that we have this technique available, we can use it to prove the following spec for sampler. This is the same as before, an instance of our interface, where here you can see the textbook definition for the expected value of f2, and here you can see the same triples as we've seen before. In conclusion, and again, we now have to populate the remaining part of the interface, that is the tapes. So as we are sampling from a single Bernoulli distribution inside of our implementation, we only have to allocate a tape for this sampler. Then the notion of ownership of a tape, we have the same shape as before. We want to own a tape for the underlying sampling of the Bernoulli distribution in a way that it's related correctly to the sequence of values we want to own at the abstract level. This ownership, this translation predicate, follows the following rules, where basically it states that for each value on your abstract notion of tape for the geometric distribution, you have a sequence of 0 of exactly this size ended by 1 on the underlying Bernoulli tape. An example would be as follows. For the Bernoulli tape, I would have 0, 0, 0, 1, so I have a 3. Then a single 0, so a single 1, then no 0 before the 1, so it's 0. And now this shows that we can implement some harder distributions with our interface. And if you want harder distributions, we have a more complicated example inside of the paper. In conclusions, we managed to specify an interface for implementing distributions and samplers for those distributions, so we can decouple reasoning about the implementation from the clients of those implementations. We have also shown a general method for populating this interface, and we have proven abstract results on samplers implementing it. Finally, we have a variety of implementations of samplers and their corresponding instances for this interface. Remaining questions are whether or not we can scale this to continuous distributions, and if it is possible in some way to facilitate reasoning about the tape predicates by maybe having a way to derive them automatically. And another remaining question is if we could get some sort of completeness result about whether or not this is always implementable, and if any sampler that does behave operationally as the distribution describes would have to obey those rules. Thank you.
We have time for a few questions. So I'll start with one. So at the start, you said you have this distribution adequacy that says if your program follows this rule, then it implements this distribution.
Yes.
Is there a reciprocal? If I have a program that satisfies this,
so that's exactly the last question I was trying to convey. We do not know if we can always hope to have such a rule if a program does implement a distribution.
Okay, I thought it was about the pre-sampling tapes, whether it's always possible.
My bad.
How does the pre-sampling of tapes actually work? Like, I mean, here you're presenting them as sort of rules, but I guess you need some kind of behind-the-scenes infrastructure in order to enable this sort of pre-selecting from a random source.
So for the primitive uniform distribution in ARIS, this is done through some erasure lemmas that tell you that if you have some behavior starting with a state with populated tapes, then starting from a state that has no tapes or only empty tapes, the program behaves the same. At least the final distribution is the same. And for every implementation, what you have to do is every time find a way to translate to a more primitive tape predicate and show that the presampling is still possible.
Can we get the next speaker ready?
So I'm a bit worried about your error induction rule, because it seems like you can only use it to prove terminating a program that uses exponential decay for termination. That is, essentially the sequence of error credits is a power of k, essentially.
Yes.
And the reason why it terminates is that the series of powers of key of 1 over the power of key is 0, right? The question is do you think it can be generalized to series which are converging but less rapidly?
So I'm not exactly sure if you could do it because this rule was already presented in the ARIS paper and I didn't really work on it, only used it. I suppose that as long as you can show that you can eventually reach 1 full error credit, then you could show a similar rule, but I wouldn't give you a guarantee here.
Is it a question or do you want?
I can maybe answer.
Okay.
So there's like different criteria for proving almost sure termination of probabilistic programs. This is kind of basic one because it's just, as you say, powers. But there are some kind of techniques based on martingales. We've also implemented some of those, but they are not part of this work.
So let's thank the speaker again.